In this video I want to talk about the Lotka-Volterra model for population dynamics, just as an example of how we can solve a ordinary differential equation using solve IVP from the scipy.integrate package. So here's the equations we want to look at. So you've got two variables, u0 and u1, and we're going to sort of think of them as being a single two-dimensional vector valued variable. And the derivative is given by this formula here. The derivative of u0 is a u0 minus b u0 u1, where a and b are constants. And the derivative of u1 is minus c u1 plus d u0 u1. So this equation was originally introduced as a kind of model for population dynamics. The idea is you've got two species, which we're going to take to be fish and sharks. So u0 is going to be the population of fish in some units, and u1 is the population of sharks. And we imagine that these change over time. Various processes, the fish will reproduce, and then they'll just sort of die from natural causes as well, maybe, and then the sharks will also reproduce or die from natural causes, but then there's also the fish eating the sharks eating the fish. And so these equations are supposed to capture how those processes play out. And so we solve this equation, we see how u0 and u1 develop over time to see how the populations of the fish and the sharks rise and fall. So the first thing we need is to define a function, which I'm going to call here du dt. So this is going to just give us the right-hand side of that equation we've written there. So you've got a u0 minus b and then let's change this to a Python cell, and then here for the second one we've got a minus c u1 plus d times u0 times u1. Okay, but of course there's A, B, C, D are all little twiddles here. That's VS Code warning me that we haven't kind of introduced these variables yet. So let's take them to just be parameters to this function here. Okay, so that's our du dt. Okay, so then we're going to solve these equations, the usual business, but let's take our we'll solve it over 24 periods, could be months or something. And we're going to take let's take 4,000 points between 0 and 24. Then we're going to do so we're going to use the solve IVP thing to solve these equations. So as usual, the first thing we have to supply is the right-hand side. And the solve IVP thing is kind of based on NumPy. It's perfectly happy to deal with vectors. We don't really have to change anything very much. And in fact, here officially I've kind of returned a list here. It's a list instead of an array. But all these NumPy-based things, if you give it a list, it will convert it into an array if it needs to in almost every situation. So that's okay. Then we need the time limits. It can be from 0 to t max. Then we need the initial position. So let's just take it here to be. Make something up. We'll say 2.9, 1.0. Okay, so these are, of course, not integers. I think you're supposed to. It makes reasonable sense for the parameters we're going to use if you think of u0 as being the number of thousands of fish. So here I've got that as 2.9, meaning 2,900 fish, and u1 as being the number of tens of sharks. So 1.0 means there's 10 sharks. And of course, we're going to be treating these as floating point variables, so they can take fractional values, which doesn't quite make sense in biological interpretation, but it shouldn't matter too much. Then we have to tell it, what the time points we want to know the solution for. So that's this np.linspace thing that we did a minute ago. We're going to ask for 4,000 points between 0 and 24. In order to see the phenomenon that we want to see here, it's best to have a kind of very accurate solution. So we won't use the default method. It turns out that this, if we hover over sol.ivp, it'll the whole thing here. And down here it tells us what's the integration method. The default one is called arc-A45, and then there's a bunch of other options which it discusses in the documentation. So we're going to do DOP853. Then we have to say what these A, B, C, and D are, and we're just going to take them all to be equal to 1. And we also have the option of specifying what accuracy we want to achieve. So we're going to say that we want to achieve an absolute accuracy of 1 to 10 to the minus 9. Okay. So now we've solved those equations, and so we do. So sol.y, actually, maybe let's have a look at. So the solution, we use sol.y, those are the actual numbers we want. That's a matrix of shape 2 by 4,000. So you've got 2 rows and 4,000 columns, and the first row is the solutions for U0, the fish, and the second row is the solutions for U1, which is the sharks. So we'll do okay, so now we can plot them. Okay, so now here you can see the time evolution. So this along we've got time along the bottom, and then up here the blue curve is the numbers of fish, or numbers of thousands of fish. The orange curve is the number of thousands of sharks. But let's put in labels, and let's kind of specify the colors we want. So now we've got the plot again, because it hasn't actually showed us those labels. As usual, we need to do plt.legend to get the labels. Okay, now it's drawn those kind of right in the middle, which is a bit annoying. So let's put the left. Okay, so we have to say upper left, not top left. Okay, so now it's put the labels in a more sensible place. Okay, so that's one way to spot it, and kind of very obvious feature is that it's kind of periodic. We see this kind of thing where the population of fish builds up, and then a little bit later, there's not lots of fish to eat, so the population of sharks builds up. When the population of sharks also gets high, then they start eating too many fish, and the fish population crashes, And then a little bit later, the sharks are finding that there's not enough fish to eat. So the sharks start starving, and the population of sharks also crashes. Now we get to this kind of point here, where we've got very few fish and also very few sharks. Then the fish population recovers, and then a little bit later the sharks catch up. So you get these kind of cycles. Another way to plot this, we can plot the fish on one axis and the sharks on the other axis. Okay, so to make it clearer, let's put in some labels again. Okay, so we labelled fish. Didn't say tens and thousands, which I probably should have done. Okay, yeah, so there we've got the time evolution of the population of fish and sharks. That's of course it does depend on exactly how much what you start with. Right here we just decided to start with 2,900 fish and 10 sharks. So maybe we can try and do a bit more. So what we're going to do, let's make a more complicated plot. So we're going to keep the same t. Or I think maybe. I think actually let's take these as t's, and then then here's our initial conditions. So we're going to start with 10 sharks every time, but we'll vary the number of fish. So we're going to start with 0.2, meaning 200 fish, and go up to 0.9, steps of 0.05. So there's this kind of varying list of possible initial numbers of fish. Okay, so now we're going to have a loop through each of these initial conditions. So I'm going to start with, then we're going to solve the equations more or less the same way we did before. Let's cut and paste that maybe. Except that here we're going to put in F0 here. Okay. Just to match up with what we had there, we need the endpoint to be at 10 seconds. And every time we start with sharks as 1, which is numbers of tens of sharks, so that's 10. Okay, so that's good. And then okay, so we've got the solution here, and then we're going to plot the fish against the sharks. Okay, so now you can see that each curve, each solution is like on a kind of closed curve, not quite circular, but a bit distorted. But you always have these kind of periodic things, where after a sufficient amount of time, the population of fish and sharks returns to where it started. I think. And there's a bunch more stuff about the Lotka-Volterra system in the sample assignment that I posted on the course webpage, but that will do for this video.